Hi, I'm Stuart. It's his fault. I am a principal offensive security engineer, and we're getting a lot of, Jesus, this mic. We're getting a lot of feedback. We used to call this a red teamer. Mostly I just fiddle around with Unix. Don't say that outside a security conference, by the way. Anyway, social media things, I don't know what's cool on social media anymore, but you probably can get in contact with me there. These are the, oh damn it, notes and such, code, whatever else. It's on GitHub. Quick disclaimer, I am not speaking on behalf of a company or anybody, just as myself. Also, we're not going to, there's no targeted pooping on products here or projects or such. Purely a high-level assumption of Unix knowledge here. Anyways, what we'll do, we'll grab a quick shell, and we'll use that just as a start to talk about how things maybe work a little bit under the hood, and then we'll get into the more offensive side. So, without further ado, here's our shell. We have a little exploit script. We can use the script to send just a command to some target. There's nothing particularly interesting. This is a BSD box. It works nicely. Our target is a Debian box, and we are running as Wurzel. We're not root. We'll catch a callback with a program called curl rev shell. As its name implies, it is a reverse shell over curl. Gives you a nice little one-liner to get a callback. Runs a little script on target, pipe it to bin.sh. Here's the code. It is more or less done. Anyways, general idea is we will take a shell. The shell will spawn a couple curl instances, one to give input, one for input, one for output. That will connect back to us over HTTPS. We'll send commands to the input side, get output from the output side. Really, going a little layer, we're just going to send standard in via curl. And we will receive the shell standard out, standard error via curl. Of course, the shell itself, all it's doing on our behalf is making system calls, the sort of thing we're talking about for the next however long. This is what it looks like. This is the, put the callback line in a shell, hit the enter button. It will send this script that goes to bin.sh, and we'll get our input, output, and the shell is ready to go. First thing we'll do is dump a process listing. I'm every so often asked, what are the malicious commands? I knew a SOC analyst who was making a list of every malicious command. This is not a malicious command. In fact, actually, this is probably the one thing that, if you're on the blue side, is a great way to figure out what malicious commands are running. Here's what it looks like if we scroll down a bit. We see that Don, probably sysadmin, is logged in. We see that we're running audit D. We have some sort of EDR going that is just, we're having feedback here. That's just watching audit D logs. And there is actually EDR that works this way. This was written at a time when somebody was supposed to be making slides. We also have the server we exploited, and this is us. It's kind of goofy looking, and if somebody also dumped a process listing this way, he might be like, what is this? We notice we're not root, we're on this Wurzel user, and we notice that we have not really run any custom code yet, and we'll avoid it. We'll mostly live off the land or under the land. Also for situational awareness, we're not in a container, and none of this that we're talking about really cares if you're in a container or not. It all just kind of works. So TLDR, we have the simple shell. We type things, our target did some things. Last year I was talking on track 1, and after the talk there was this group of people asking questions, and a fellow sort of at the back of the crowd was just kind of looking at me, and somebody in the front was like, hey man, what's with the blue moose? And I said, well, actually it's a TLDR, it's a teal deer. And the gentleman in the back just kind of looked at me and left. So yeah, if you're here, sir, this one's for you. It's a teal deer. All right, so a bit of theory here. Back to our shell. This is us. If we say we are on target, we are the target, we are hacking, we are a shell process, and we run commands. And in this case, our command, it spawned a program. And most of the commands you run really are programs. The shell itself is just a program. And let's shelve that and let's talk about sort of what we're doing with these programs. I'd say the bulk of what I do on a Linux box is try and access data, read files. Here's a file. It's not a file and disk file, but it is a file, and it has environment variables for our vulnerable server. And the general way to read a file, you cat it and you get output, which is good. We can do slightly better. We cat this, and let's look at what's happening under the hood. So we'll strace it, and strace just prints out a list of system calls. I had a very angry bolster coming towards me for a second there, because it's shell stuff right away. Anyways, we see argv, and argv is not the command line. It is called the command line, and you'll see in certain defensive tooling, this is the command he ran. Well, not actually. This is the dev null thing, if nothing else. But actually, the bit we're interested in, the bits, is that curl for us opens a file, it reads the file, writes the file. These are system calls. These are the interface between us and kernel. System calls which are somewhat hard to read, we can dig in for those who are less familiar with them. We'll take the registers, and a system call really is just sticking a number, usually an REX, and some arguments, the file descriptor for the directory, or -100 for we don't care, a path name, which is just a location in memory, a pointer, just like how far from the beginning of memory we're going, maybe some flags, read only, and then we hand that over to the kernel, and the kernel is like, somebody has called a system call. It is system call 257, he would like to access this file. It'll update a state table, a metaphorical state table, probably several of them, allocate us a file descriptor number, and return that to us in RAX, and then we get that, and we're like, we have opened a file, we have file 3. So from our end, we're like, all right, if we want to talk to the kernel and do things with this file, we use 3. The kernel's like, hey, if he says 3, he really means this inode device pair. And that is kind of how system calls mostly all work. Read will be similar. We say, hey, system call number 0, which is the read system call. We want to read from file descriptor 3, whatever that is open to, and we don't really care. It's just, it is a file descriptor number. I mean, we opened it, so we care, but really, it's a file. We could just say, here, stick some bytes in that buffer, this many bytes, up to this many bytes from about here-ish. Hand it off to the kernel, it returns to us. It's like, I read 454 bytes, and our buffer is suddenly full. And write works pretty much the same way, except we'll use file descriptor 1, standard out. And where that is going, if we, for some metaphorical we or cat, we don't care. Anyways, returns us, and it looks like that. And it turns out Linux ops is really just loads and loads of system calls. There's a whole bunch of them. Here is a table. There are many. Link to it there. And pretty much everything we do really is just a lot of these system calls. Okay, so here's our EDR logs. And we'll tail them. And of course, tail prints the last n number of lines, 10-ish or whatever. And just to make things interesting, we won't just tail the file. We'll actually echo the string tail procrastination edr.log to a shell and run it. And we'll see that we do get shell output, or excuse me, tail output, EDR logs, severities, commands that were run, et cetera. If we do that with strace and see what the shell is doing under the hood, first we see that the shell is executed, okay, as you would hope. And the shell, all it does is another read. So all these commands, really it's just, what is a command? I don't know, standard into a shell. The shell will parse it and figure out what to do with it. In this case, the shell is like, I will start this tail program as a result. Looks for tail, finds it, starts it, forks off a new child process and execs tail with the file to tail, which then, of course, does an open, a read, a write, et cetera. That works. And then we have now, mostly we've just been reading, writing file descriptors. Kernel doesn't care. It's like, okay, file 1, I'll send it to you. We don't care. It's like, hey, send it to file 1. And all of these pipes, or excuse me, all these programs are just connected by file descriptors, our curl, our shell, whatever else. If we list some files, if we list dev fd0, fd1, fd2, those are kernel-provided links to our file descriptor 0, 1, 2. We will use that later. And we'll also list the file descriptors, the open file numbers for the input curl, the shell we're in, $$ is the pit of your shell. And the curl we have, oops, we'll hit the button twice. So there's our shell, and we see that it's fd0, 1, 2, and ls is inherited from the shell, is these pipes we have open, and these are the pipes from curl, 0, 1, and 2. So that's a nice, neat thing you can use as devfd sometimes. If we look at the relationship between the input shell or the input curl in our shell, we see that, yep, input curl's standard out is piped, and it is the same as shell standard in. So we could maybe abuse that, or just use it to hide a bit better. Same with shell's standard out, standard error. But that is interestingly going to file descriptor 3, not curl standard in. And curl does look a little funny. So we have a sysadmin on the box we saw. He will echo ID to the input file descriptor, or rather the pipe going in, and the shell, I mean, curl doesn't care. It doesn't know that somebody's writing to its pipe. The shell is like, oh, somebody wrote me an I, a D, in a new line, and so the shell just runs it. It works. Likewise, our sneaky sort of trollish sysadmin can write to file descriptor 3. It'll write to curls 3 here, which seems to be where our output is going, and yeah, we see the output come up through the network and into curl rev shell. So you can use this when you want opens to happen in one place and reads and writes to happen in others. It's actually really handy escaping containers. You like get your shell spawned outside the container, but then you have inside container file descriptors that are hooked up to you somehow. Just use them. Of course, this is our turtle in the pipes doing strange things. Slightly more graphically, here's what happened is Donatello sent the ID to this pipe, shell did things, sent it out, likewise sent text straight to curl and out. Quick aside, I find that OpenBSD's ktrace is easier to use for visualizing system calls. Give it some complex-ish command and it will tell you, aside from running it, it'll tell you what happened. Kdump will dump the output of the file. A little easier to read, I find. IO is definitely easier to read. And then if you're just interested in command line arguments, it is slightly nicer there too to see. Cool. So here is our EDR. Let's talk about this quickly. This is not based on any real product, but all it really does is tail audit log, and you could replace the whole thing with a Perl script if you want. An EDR largely is just regex in a trench coat. It will look at command line things and be like, oh, you have matched it. Look, somebody ran sudo, that's priority 2. Somebody ran not sudo, that's priority 5. The EDR, by the way, has no response actions. It is just ED. It works better than some ED. And for the people snickering, I meant this ED, not that ED. Anyways, my own observation is the blue team, speaking of syscalls, really likes execve. They like to see what we stick in execve and do regex on that. So we have tailed our log. We see that. Let's run this program called which will tell us the paths to programs. And it is itself a standalone program, user bin which. It didn't find type, though, but we stick type in our shell, and it will tell us, as a shell built in, that type and echo is a shell built in. So we have 2 echoes, one shell built in and one not. If we use the shell built in, it will just cause the shell to make a write to standard out. And that will be nicely invisible. If we use bin echo, which is its own program, which now has an argument vector, because it's called execve, that will be visible. Look at our EDR logs, and sure enough, the visible one is visible, the invisible one was invisible. So we can do a bit of evasion here. We can make read and write system calls and whatever else, as long as you avoid an execve. It's good enough for the theory, I think. Let's start hacking things. But TLDR, we just need the right syscalls in the right order to do strange Linux ops. Cool. Mentioned we're not root. So, and the reason we're not root is because it's just easy. If you have root, you can stop your EDR. You can say, yeah, I can run sudo and kill. I can run this as root. EDR is running, it sees us run sudo, does not see much else, and we can see that our EDR is in the sleeping state. This is a EDR SPID, sure. Send it a sig stop. Kill does more than kill. Kill sends signals, and the stop signal does not kill, it stops. And yeah, EDR is stopped, sure. We will echo something that should be visible and find out it is not visible, but the stop was visible. If we want to undo that, send it a continue, and then we can see things. So TLDR, there is no point in doing any of this as root. Just stop your EDR. Works pretty good. There is also a shell built-in kill. So if you have a standalone root shell, just use that without forking a kill process. Pardon me. All right, back to, see my taskbar, my menu bar. Back to this. So like, we are hacking a box. We would really like to grab things. The easy way is cat. So we look at the mounted file systems. We see mounted file systems. Of course, we see that, then SOC sees us seeing the mounted file systems. That is not great. We can do better. We can redirect it in. It's slightly sneakier, and we'll look at the TCP connection table, hexed and backwards, but sure. And we see that, and that's less visible. We still have a cat there. If we look at what was happening there, we'll trace a shell running this cat redirection. We see that the shell, before we fork an exec, the shell is dead open for us. Hooks up file descriptor 3, procnet TCP to standard in. Then it forks an exec's cat, and cat does not care. It's kind of a theme here, does not care. It just reads and writes from in and out. We get what we want. All our files, all our data comes to us. The syscalls are all made in the right order. We don't really care what made it. Do one better without having to exec a cat. That's terrible. We can look at the ARP table, the MAC addresses the box knows about, and we'll use read, and read will just read a line from standard in, or whatever you tell it to. Every time we read a line, we'll echo it, put it in a loop. We see our ARP table, but we can do slightly better. We can look at our network device list, pipe that in. Normally, $ curly braces is a command, but put a dollar, put a left angle bracket there, it'll slurp a file. And we can echo that out, and that would also nicely read without any sort of fork and exec, unless you're on a Debian target and you're using the Debian Almquist shell, I think. And then you don't get that, but we can just exec bash and go on with life. look at the com. Com, by the way, is the process name as much as you get a name, and that works. So now we have nice file read, write, no fork and exec. Excellent. And you can use this, you can almost like implement core utils. Say you want to find out two files have the same contents, kind of like diffing them. If an interface index and interface link index on the interface are different, it is a veth pair. It's helpful if you're in a container. Same thing, just read them in, check it if it's the same. If it is, echo a message, and yeah, we find out that's a veth pair. If we want to look at the mounted file system, say, but we want to find if there's one that has read write and not no exec, not no execute, i.e. somewhere we can drop some tooling to run. Same thing, we'll just re-implement core utils, we'll re-implement grep. It works, but it's a fork and exec, or it's an execless grep. It's all the system calls from grep minus the unhappy ones. Also a little faster, works nicely. Cool, so mentioned a while ago, we're running curl rev shell. I did not mention that we have some strange flags here. This control I is tab. You can tab in a script, which means you don't have to type things so many times. If we were to write, say, cat, our own xcat, extended cat, if we re-implement 4 util or more utils, if we implement core utils and write 4 of them, we'll get 4 utils. Anyways, put cat there, tab it into the shell. Now that is just run as shell input, and all the shell commands is just the shell reading, right? Yep, cat it out. Now we have a nice cat, except shells don't particularly like null bytes in your input, which is not so great. Okay, yes, thank you. Do the same thing with read, except read with a D and a empty string. We'll read up until null bytes. So it's kind of a way to translate null bytes into new lines without using TR to do it. Run that, and yes, we get the same environment nicely formatted without whining about null bytes. Likewise, use it for a process listing, minus exec. Also, by the way, the tab doc thing prints you a nice little tab list, little function generated, little creature comfort there. Anyways, so we had our situational awareness, we dumped a process listing, and I was like, hey, this is not a malicious command. There is actually a tool out there that will call the PS, oh dear, this thing malicious. I disagree, but nobody asked my opinion. Anyways, the XPS that we had, the loop, the read in a loop that will not exec, looks like that. It's pretty close. And if we look at what we've been doing the whole time, we see that, yeah, no, we're not actually visible in EDR at the moment. Cool, so some shell gymnastics, quick recap. All we really wanted was the kernel to do things, and it will do whatever it gets a system call to do, a system call, and external programs just make more system calls. EDR sees those, so we make syscalls, kernel does things, don't make the wrong ones. Switch gears a bit, talk about networking. So we can do, this is what we were doing, shell standard in, a bunch of math, do TLS, shell standard out, et cetera. I was like, hey, we'll look at that weirdness from curl a bit later, which we will now. The top curl, the input curl, is relatively normal looking. Kind of complex, some certificate pinning there, but relatively normal looking. But this bottom one is not. And I don't think anybody believes it's actually connecting to something normal. But it has this flag K, and K will take input from standard in and run that as a config. Original curl, we ran this to get it. Here's what it did. It printed us a script. If we format that nicely, we see the top one is just pretty typical curl. The bottom one, typical curl, the bottom one is kind of where it gets interesting. And this is where our, okay, we just care about file descriptors and syscalls comes into play. We took file descriptor 0, standard in, and duped it to file descriptor 3. So we hooked up file descriptor 0 to 3, and so we can now use file descriptor 3 to read whatever came from our shell, which frees up file descriptor 0, standard in, for a here doc, which is kind of a buffer filled with data, to pass in config. And the config called us back, did certificate checking, uploaded a file, so on and so forth. And that's a total red herring. We're just like, hey, pretend that's a file, curl. And curl's like, yeah, I couldn't read it, or whatever. Shows up in a process list, though. So that's not bad. We still have a minus K. We can do a little better. Say we want to use curl as a port scanner. Make sure the config file is not there, and we'll just drop a config file to disk. So there is no file in temp. So we'll make a config file in temp. And shell globbing, another syscall that the shell will do for us, it's get directory entries. And we really care if the temp directory has a directory entry that's curl RC. It does now, but the shell filled it in for us. Nice. There we go, there's the config. We are going to connect to this box on all 65,000 ports in parallel very quickly. Port scanner. One more thing, the time is a shell built in, time keyword. And we'll use that in a second, but we'll run curl. set its home directory to temp so it knows where to find curl-c, and then just search the output for connected, minus an exec. There's a fork, not an exec. And time, because it takes quite a bit of time to do this, and we will want something to tell us when it's done. Hit the enter button. We find that we do, in fact, have ports, and then 2.5 minutes later, it's like, OK, I'm done. Also, it means that the Belfast, or the Dublin to Belfast train's Wi-Fi did not drop out on me. That was a very large relief when that thing finished. Anyways, we do a little better. So that still puts curl in the process listing. That still means we have to exec a curl. But really, we just care that somebody's going to call socket, system call. Somebody's going to do a socket, a connect, so on. And the shell will do that. If we redirect in from dev TCP, at least in Bash and some corn shells, I think, dev TCP IP port, it'll do a connect for us. So we'll just read a line from that and print it out. And we see that, yeah, some other box has Debian open on port 2 for keeping my logs quiet, not actually a security measure. So stick that in a loop. The colon there is a program or shell built in, I forget which. It just returns true, but it's a way to, if you just want redirection happening, you just have redirection happening, but it will still return like unhappy if it fails, so you'll still get the ampersand echo p. Stick that in a loop, background it, importantly, because it will take a little while. Also, it means if you background it, you still have your shell when it's sitting there finding ports, and it's just a little faster. Takes just under a minute. Look at our EDR logs, and we see that, nope, all we had was curl and nothing else. The curl from up here and nothing else. I do also, besides red teaming, a bit of purple teaming, and sometimes it comes in handy to have like a lot of EDR events or a lot of process execution. So we can run cat, and we use cat instead. So not only do we get a port scan, which is sometimes visible in tooling, we'll get like 65,000 executions of cat really fast. It's good sometimes to check your EDR's comms. There is actually one more benefit. You can tell your SOC that you did a cat scan. Mrs.
It's not too late to cancel you.
Man, I would have been canceled so long before. Actually, I've been watching the back door because like we're coming up on lunch, and nobody has left yet. And as I was saying that, a gentleman was like, thank you for turning around. My ego is better, though Mrs. McMurray would say that maybe you shouldn't have helped my ego any. Anyways, networking TLDR, we would like to connect and send data. We don't really care about much else. All right, general idea with curl was this, which is cool, but say we take a shell, say we stick our own code in the shell, and that little bit of code we stick in there does the networking things for us. Shell will still do the syscalls, but we don't have the curls. Oops, we don't have the curls anymore. It's a little even more sneakier way to do things. Okay, so let's write it real quick. We will write a little C program, little C function, a constructor function. All a constructor function does is when a library is loaded, it runs first. And this constructor function will connect standard I/O for us. And actually, that's just going to call another function we'll write here in a second, which, believe it or not, is connect standard I/O. And that will connect to our server, taking URL and a fingerprint. And this is doing quite a lot of heavy lifting. And we'll have to pass in the URL and fingerprint. That's easy. But anyways, it connects, and error checking as required. And then we'll hook that up to the standard I/O from within the shell. From within the shell, we'll take the file descriptor of the connection and connect that to standard in, plus types because this is Go, plus error checking, as well as standard out, standard error, with the idea that we only need a shell process. We'll build it, which is somewhat of a, not that easy. Anyways, there's the files. Please ignore the ones we don't need quite yet. Build it, pass in the URL, the fingerprint, et cetera. We do, in fact, get a dynamically linked shared object file. It's 6 megs because we wrote this in Go. It's quite large, and we can't really just copy paste to target anyways, but we have shell built-ins, right? We can just, a little Perl script to encode anything to a bunch of printfs. Printf has a shell built in. It will open a file and write bytes to it. Open, write, close, hopefully. Truncate it first. So we'll just encode our entire library in a bunch of printfs and stick that. And we'll printf it to the same file we've been using because it's there, might as well. Hit the tab button. If you're going to do this, sending 30 meg of printf commands is not a fast thing. And this was actually where on the train my Wi-Fi dropped out, by the way. So yeah, if you're going to do this, type echo done, hit the enter button, so that way at some point after you've fallen asleep, you'll get a done and know it's done. Also, if you're going to stick this in that control I directory, remove it later so you don't do something, hit tab, and then like 2 minutes later you're still waiting for it to finish. Anyways, we'll set up a catcher. It'll catch it on 5555 this time because 4444 is already in use. It's listening, and we'll run it this way. The enable program or enable shell built-in says, hey, bash, there's some shell built-ins in this library for you. Go load this library. And bash will do it. And we'll stick that in a subshell, parent shell, subshell, and then the actual bash. The nice thing is that middle shell, the parens here, will terminate. And so we'll have less relation between our two shells. It's just, we called fork twice instead of once. Hit the enter button. It did call us back. Bash whines that this library.curlrc in temp is not actually a proper library that contains shell built-ins, which is good. You can make the enable whining not happen, but it's nice to see that it actually did something. Run a PS, scroll down to the bottom, and yeah, we see that now we have bash, which if we were not running PS would just look like somebody's script broke. And it's just sitting there. Of course, it also is kind of strange that we have a very large bash. But anyways, that's us now. Dump the file descriptors for our shell. We see that's a bunch of sockets. So now we're doing well. We don't have pipes to anything else. We don't have a file that was a script we've read or whatever. We do actually just have bash talking to us, which is excellent. There's one slight catch. If we look at the mapped memory, and this is memory that either we've just asked the kernel with the mmap system call, hey kernel, I would like a few kilobytes of memory, or hey kernel, I would like you to take this file, like this file, map it into memory for me, and I'll just read memory, and it actually does file things, which is an even less syscall way of doing reads and writes. And we see that, well, that's not really meant to be there, and we definitely don't need an executable curl config file mapped into bash's memory space. It's a little weird, but we have a plan. So we can get around this nicely if we mmap ourselves a buffer, copy data from each of these mapped regions to the buffer, and then very quickly mremap the buffer back over. Mremap remaps it, and since the buffer is now occupying that memory space, the kernel's like, oh, I guess the file's not, times 5. We'll do it this way. We have, it is in a library. There's a link to it because we're almost at time. So we won't read the code, but we can just load the library. And all we have to do is load the library. It has a constructor function that'll do all the remapping for us. That is the library. Nice thing about Go is you can drop this somewhere, and if you want it, add a build tag to add it. If you don't want it, don't do that. Also, we'll stick in a quick little unlink, a remove to remove our somewhat strange shared object file now. And finally, we will set the debug flag just because it looks cool. So compiling is the exact same way. Printfing, hitting the tab button, waiting works. Same sort of enable, except this time, bash loads our library. Our library says, I found these mapped memory. I will unmap them for you. And it remaps them, remaps, unmaps. We are invisible. And we can then see that in this massive memory map that Go gives us, bash is by itself is like half of this. There is at least not anything there. And you can verify it using the same kind of not so great grep. Also, our file did delete. And now we are somewhat hidden. The minimum of fuss. Anyways, TLDR, if we take a look at Linux ops, they are really just series of system calls plus shell output, that guy's fault. And then if we look at like, okay, cool, what's stealth or noisiness? Well, that's really just the wrong system calls or the system calls that are unnoticed, depending on your look at it. And so if we want things to be easy, just don't be fussy about the tooling. 90% of the toolkit I use for most of this is just curl and bash, or whatever shell is on target. And the other 10% is whatever's there. And actually the reason I wrote curl ref shell and curl is because I was like, well, I would like something that does socket bind, connect, et cetera, and a bunch of math and a bunch of read writes. What does that? And it's everywhere. So that's curl. TLDR, important thing for all Linux ops, system calls. Thanks. Do we have time for questions? Yes. Questions? Was that a question or were you waving?
It's a vague question.
A vague question.
At one point you did exec bash
At one point I did exec bash
instead of just bash.
instead of just bash.
Is that important?
It is, there was a reason, yes, and the reason is exec in bash does a few things. It'll move your file descriptors about, but it will also replace a process with another process. And that's how fork and exec, split a process, exec your new program. Because if you don't exec bash and you just bash, then you have this like, shell spawns curl shell, shell spawns shell, and you get these like massively long process trees. That is why exec bash. Yeah, good question though. Any other questions and or lunch? None.
I think we can read the room, so I think everyone's getting. I can hear everyone's stomachs churning. So let's give Stuart a round of applause before we let him leave. So final thanks from me on track 2 is thanks again to Rapid7 for supporting the subtitling, which hopefully helped in the low audio. Go for lunch. If you want wristbands for the after party, follow the black duck, and enjoy the rest of your day.